Okay, good afternoon, ladies and gentlemen. As I promised, we're going to go over the problems in the textbook on page 147 to help you prepare for practice D. So I'm going to review the first one real quickly and show you the solutions that I had with the correct mass. It says there's a clock initially at rest on a horizontal floor. It requires 650 newtons horizontal force to set it in motion. After it's in motion, you only need 560 newtons to keep it moving with constant velocity. So it wants to know the coefficient of static friction and it wants to know the coefficient of kinetic friction between the clock and the floor. All right, so here we do. Here's what I do. I always rewrite what it is that they're asking for. Tells me the mass, tells me Fs max. So there's the force you have to have static friction to overcome to make it start moving, 650 newtons. And then once it's moving, now you only need 560 newtons. And it wants to know what is the coefficient of static friction and the coefficient of kinetic friction. All right, so I draw a block diagram, and this is sitting on this blue line right here, sitting on this line. So I have mg is the force due to gravity pointing down, and I have the normal force. Well, in order to be in equilibrium, those two forces in the y direction have to be equal. So I know that down here it's negative pointing down, and up here it's positive. So it's going to be the 95 kilograms, times the negative 9.81. The magnitude we care about is 931.95 newtons. Okay, so definition. We've got that mu sub s, or the static coefficient of friction, is the Fs max divided by Fn, the normal force. So here it is, 650 newtons divided by what we decided these to be, 931, and there is my static coefficient of friction. And my kinetic one is just Fk over Fn. So you're always going to need to know what the normal force is in the denominator. So I put 560 newtons divided by the same thing, then the normal force, and I come up with 0.6, 0.7 and 0.6. There you go. All right, let's read the next one, number 36. Big, huge book. There we go. A box slides down a 30-degree ramp with an acceleration of 1.2 meters per second squared. Determine the coefficient of kinetic friction between the box and the ramp. Okay, so I have to draw a picture. Plus you get credit for a picture. So let me see, I started drawing the ramp here for you already. Here's my ramp. Okay, so first of all, let me write down what it is that they told us. They say that it's 30 degrees. There's my ramp at 30 degrees. And they say the acceleration, so I'm gonna write that up here. The acceleration is 1.2 meters per second squared. So it's sliding down, it's going down this way. All right, so let me move this huge book out of the way. Here's my, let's see, I'm going to unzoom it. Okay, so there's our block diagram. And this we're doing here is number 36. There it is. Okay, so we're going to have to draw all the forces. This is why it's a good idea to draw it big enough for you to be able to see everything. All right, so I see this guy has a normal force. It has to be perpendicular. So on this axis, I'm going to draw a little imaginary axis here. I'm kind of drawing dashed line here. And I see that the normal force is going up. Okay, that's the force of the surface pushing up. This is my normal force. And I know you saw that they use N. I'm used to F sub N, so we're going to stick with F sub N. And this is the axis that we care about, mostly because it takes care of some of the forces that are on these axes. If it's sliding down, therefore, the force of friction must be in this direction, going up. This is the force of friction. Now, there's two different kinds of forces of friction, the kinetic friction and the static friction. All right, now I also know that this guy is going down. I'm trying to make it bigger for you guys to see here. So this guy has a down force. Let me see if I can find my purple marker, or purple pen. And I have the mg. The mg, that's the force due to gravity of this guy. So that's going to go perpendicular to the surface of the ground. So let's see, right here. Here we go. This guy right here, That is my mg, my force due to gravity. Okay, so I need to break this guy down in terms of its vector components with respect to the axis that we care about. I'm looking for my highlighter here. All right, so here's why I was so hard on you guys. Make sure you point in the right direction because it's going to matter. I'm going to recognize that the y component is this guy going down. Here's my y component of this guy. So this guy is like the hypotenuse of the triangle. There it is. So this is f of g in the y direction. It's pointing down. And in the x direction, it's this one, horizontally. This one, and it's going to the right. So that's f of g in the x direction. All right, so notice I have three forces. Let's see. My force of friction, my normal force, and I have f of g. But now I can ignore this guy and only care about the y component pointing down, and the x component pointing right. Because when I add those two vectors, that gives me the f's of g. All right, so if I ignore this guy because I'm already taking care of him, these two, now you can see a total of 4 vectors. 2 horizontal, see this one going horizontally this way, this one going horizontally that way, and 2 vertical, the fn and the fg in the y direction. So if you think of tug of war, and it is balanced because it's not flying up and it's not flying down, then you have to recognize that the magnitude of the normal force has to be equal to the fg in the y direction. Again, this magnitude going up is equal to the magnitude of this vector going down. So do they give us the mass of this one? No, they only gave us the acceleration. Okay, and they want to know the coefficient of friction. All right, so what they asked for, it's a good thing to write down. They want to know the coefficient of kinetic friction. So I want to write that down. I want to know what mu sub k is. That's what they're asking for. Then I look it up and I'm like, oh yeah, that's the one with the f sub k over f sub n. My normal force in the denominator and f sub k. K because it's already moving. Okay, so it's already moving. It's already moving, so therefore the force of friction here is my kinetic. I'm going to change this to a K. That's my friction. Okay, so what we're going to look at is the components. I just told you that because these guys have to be equal, then I realized that f of n, the magnitude of the normal force, has to be equal to f of the mg in the y direction. And what is that? Well, I know that this is 30 degrees. So I know that this guy in here is 30 degrees. Okay, that one there is 30 degrees. All right. And I showed you guys the proof so you can hopefully look at that handout. This is 30 degrees. Okay, well, if this is 30 degrees, and notice how the fg sub x is opposite to the 30 degrees. And by the way, this guy here is just mg. They didn't give us the mass. Whatever the mass is, we're just going to say it's mass m times g, and that's lowercase g, negative 9.81 meters per second. So f sub g in the y direction is going to be the other one. So I better write that down for you. Let's see. I write here f sub g in the x direction I saw as the sine one. So that one's mg times the sine of 30. And the other one is the adjacent one. F sub g y is mg times the cosine of 30. And that one happens to be the normal force. Remember we said that this has to be balanced out, has to be the normal force. So this one happens to be the force, the normal force. All right, so that takes care of our y direction. Now notice we have to have some balance. Then we'll notice that we have a net force because it's coming down. If it wasn't moving, it was just starting to move, or if this was the static, then the force on one side has to be equal to the other side. All right, so it's not, it's moving. So I have a net force. So let me unzoom a little bit here, unzoom. So I need to have a net force. Okay, so I know I have a net force. And in the x direction, this vector here, well, I could easily draw it up here. It doesn't matter, right? All we know is it has a magnitude and it has a direction. This one's positive. So my net force has to be this one right here. I'm going to draw it here. F sub G sub X has to be this guy. He's in the positive direction, and I can add it to this guy, which is the one in the negative direction. All right. So I'm going to say here F, this guy minus that guy. So the force, the net force has got to be the F sub G in the X direction minus the kinetic friction. Make sense? Because I got this guy in the positive direction, I got this guy in the negative direction. But what else do we know about net force? Well, it's the mass times the acceleration. So that's what we know. We know two different equations, that the net force is the mass of this box times acceleration, which they gave us. But looking at the vectors, I have a net of this force going to the right on the x-axis and this force going to the left, also on the x-axis. Okay, so what do they give us? They gave us, well, we figured out that FG is this guy right here. So this one here is mg. All right, mg. Why do I have 0.5? Oh, because sine of 30. Sine of 30 is 0.5, right? We know that sine of 30 is 0.5. So just to make less to write, I know one of them, sine of 30, cosine of 60, I think it is. All right, so I'm going to say 0.5 mg, just less to write. So that guy goes here. So I've got 0.5 mg minus f of k. All right, minus f of k is equal to the mass times acceleration. Here's my mass, and they gave us the acceleration, 1.2. 1.2. I just realized I should have just solved for the variable, but oh well, here we go. Okay, so what do I have here then? I have the force of kinetic friction. I'm just going to solve for this force right here, my force of kinetic friction. So I'm going to, what do I do? I'm going to add this to this side and subtract to that side. Well, you can do it the other way around too. You can just subtract this, but then you have this guy negative. So I'm going to subtract this guy and add FK to the other side. So what I end up with? I end up with 0.5 mg, and then, oh, I should have said minus, sorry, make this mg minus m times 1.2 meters per second squared is equal to fk. Yeah, I want to solve for the friction kinetic because that's in my numerator, because I already have, I can figure out the Fn, which is going to be equal to this guy right here. All right, so I added fk to both sides, made it come over here, and then I subtract all this guy this side. Now, sorry, it's messy. I'm going to rewrite it so you can see it more clearly. Mg minus m times 1.2 meters per second squared is equal to fk. Now, notice that there's an m in both terms here. How convenient. So we can factor out an m. Let's factor an m, and I have 0.5 g, which would be 0.5 times negative 9.1. Oh, there we go. Minus minus 1.2. That's what I should have done. Negative 1.2. So here I've got meters. This is kilograms. The m is kilograms. This is kilograms times meter per second squared. And here I have kilograms times meters per second squared. So I pulled out the m. So I have 0.5 g. Sorry for this line right here. Minus 1.2. And also meters per second squared. So let me rewrite that, guys. I'm going to take off the units. M times 0.5 g minus 1.2. How's that? Minus 1.2 is equal to your f sub k. All right, there's my f sub k. So why don't I just replace all that up here and take my Fn, all this right here. You'll notice the n's are going to cancel out. All right, so f sub k, I'm going to rewrite that up here. I got 0.5 g minus 1.2. All that times m. All that times m. All right. And my Fn, here's my Fn, mg cosine 30. I'm going to say g cosine 30, all that times m. The point is, this is always going to be true no matter what the mass is, because the mass cancels out. All right, my mass canceled out. You guys see that? I took this guy right here for Fn, I put that in here. And I rewrote it so the m's would cancel out. And this guy here is 0.5 g. So let's plug that in. I've got lack of room. Here's what I have. I'm going to put here 0.5 times 9.81. We're only interested in the magnitude because we already took care of the direction by saying who is equal to who. Minus 1.2, all divided by negative 9 or 9.81, sorry, times the cosine of 30. That's what this is equal to right here. All right, so when I canceled all that out, I get 0.436. 0.436. 0.436. You guys can verify that. 0.436. Okay, so let's review this problem. This problem was interesting because they don't get you a break. They don't give you the mass. You can just plug in the mass. But the point is, because all you needed to know was the acceleration and the angle, and because of how fast it's going down, you can figure out what the kinetic coefficient of friction is. Okay, so what do we do first? We looked at our y direction vectors and we realized that the normal force is equal to the mg force times the cosine of 30. All right, so I'm going to turn off the light here. See if that's better. That's better. All right, times the cosine of 30. And then we had to figure out what our x in the x direction was. We had a net force. So we have the positive one, which is mg in the x direction minus the fk. That's our net force, and that's equal to mass times acceleration. Okay, so from here we saw for what fk was. You guys work on this right here. It's a little confusing because I put the units in here. I took off the units here so you could see m times the quantity of 0.5 g, which you could have figured out what that is, 9.81 times 0.5, all that minus 1.2. That's my fk, that goes upstairs here. And then my fn we got from the fg in the y direction, mg cosine 30. All right, so there you go for number 36. Let's see, for number 37 is really interesting. And I tell you, I struggled with it because I didn't understand it. If you can't understand a problem, you can't solve it. So, and my husband actually demonstrated pushing something on a ceiling. Then I could see what the problem was. All right, so let's read this one. This one's really fun. You have a 4 kilogram block is pushed along the ceiling, the constant applied force. So what's weird here is that here's your ceiling, here's your block, and you're pushing up. So notice you can draw your vector wherever you want. So really my hand is probably right here, taking that block and pushing it. He did it over here on the door jamb, and I could see. So you're pushing up along the wall. That's what's happening here. 4 kilogram block is pushed along the ceiling with the constant applied force of 85 newtons. So look at, we're pushing it up. That acts at an angle of 55 degrees with the horizontal. Of course, there's an angle, because if you push it straight up, it's not going to move. You have to push in an angle to have it move across the ceiling with the 45 degree in the figure as shown. The block accelerates to the right at 6 meters per second squared. So they give you the acceleration, and they want to know again, what is the coefficient of kinetic friction between the block and the ceiling, because it's already moving. All right, so you guessed it, we have to draw vectors. All right, so I'm going to start with a fresh piece of paper here. Okay. Really should have given myself more room on this table. Okay, so let's see, here we go. We have, I'll draw as big as possible here. Here's our ceiling. He took my cell phone, he was pushing it along the door jamb, so I finally could see what was going on. So we're pushing it up. So we can show the vector this way, even though your hand's probably over here pushing it that way. It doesn't matter where you draw it. Okay, we're pushing it up, and it's 55 degrees with the horizontal. All right, so that's my force. And they told us it's 85 newtons. I'm looking at the book here. 85 newtons. So this guy here is the force, and it's 85 newtons. I'm already wishing I drew it bigger. Well, it'll look bigger if I zoom it in here. All right, 55 newtons. What else? They gave us the acceleration, and they told us the acceleration is 6 meters per second squared. Okay, and of course, you happen to know that little g, acceleration due to gravity, is negative 0.981 meters per second squared. And they want to know, what is mu k? What is mu k. All right, so first thing I would do is go, well, what is mu k anyway? Mu k is, I know that it always has the normal force. So it's the force, kinetic force on the numerator and the normal force on the denominator. Okay, so I'm going to draw wish I'd drawn this bigger. I am going to draw this bigger. All right, so here we go. We're going to draw this much bigger. I'm going to draw this bigger so I can really see more easily. That's supposed to be straight. 85 newtons. And here's my horizontal axis. And this from here to here is 55 degrees. All right, so since you're good at breaking down the components, I'm going to go ahead and write down the components. I can see going up, I have in the y direction, f of y here is, this is the one that's opposite the angle. So this one's the one that's a sine. In this case, if 85 sine of 55. Okay, and in this direction, I've got f of x. F of x, this is my f. Here's my f of y, here's my f of x, and this one's 85 cosine of 55. All right, what else do I have? Well, I know that this guy, even though he's hanging, being pushed down there, he's got weight. He's got a force of weight. All right, so whatever it is here, the force of the weight. Okay, so we have the force of the weight. Now, guess what? Because you're pushing up on it, you're pushing up on this surface is pushing back. So how about that? There's also a normal force, and the normal force is going down. Isn't that interesting? So I have a normal force. So how do I show another force? I don't know, I want to show it. I guess I can show it next to it, huh? I'll show another one next to it. They're really supposed to come from the same dot, but I just want you guys to be able to see what we've got here. So I've got a normal force. The normal force is always going to be against the surface that you're pushing, because you're pushing up by this much. There it is. And you're also pushing to the side by this much force in newtons. So we have the mg going down, but we also have the normal force. I could have shown it as one vector is the normal force, and also it has and a normal force, but that gets a little confusing. That's why we're going to show it like this, because we do have two vectors. All right, so now let's look at this. I need to show, where's my equilibrium? Okay, well, there's equilibrium in the y direction. Otherwise, it'd be going through the ceiling or falling down. So you notice I have two vectors going down and I in the y direction, and I have one vector going up in the y direction. It doesn't matter where I draw it. I could have drawn this f of y right here. I could have drawn it there. So your eyes have to look to, where are all my vertical ones? So I can see that this magnitude, the f of y1 magnitude, has to be equal to the magnitude of these two put together. What do I mean by that? That the normal force plus the gravitational force is equal to the force, the applied force. This is usually called applied force, APP. So this could be the applied force in the y direction. The applied force in the y direction. All right, so we know that FG is always mg. We know that. That's always going to be the case. So this guy right here is mg. Okay, the force applied in the y direction is 85 sine of 55. So this is just a number. You already know that one. It's right there. 85 sine of 55. So we need to know what the normal force. Why do we need to know the normal force? Well, if we're going to figure out the coefficient of friction, I need to know what the normal force is. So the normal force is, I might just have to subtract this guy to have the normal force by itself. All right, so I'm going to do f of n, moving over to the left here, is equal to f applied in the y direction minus the mg. That's going straight down. Okay, so that guy is 85 sine of 55 minus mg. Good? All right, and they didn't give us the mass here, did they? Oh, they did give us a mass. You guys. They gave us the mass. It says here, 4 kilogram block. Isn't that nice? They gave us the mass, so we can start plugging stuff in. All right, so the mass, let me go ahead and figure out here. The mass, should have written at the top, mass is 4 kilograms. All right, so therefore, F of G is mg, is just 4 times 9.81. Okay, I'm looking for my calculator. I can just plug that in there. 4.4 times 9.81. Okay, 4 times 9.81, 39.24. 39.24 newtons. So this guy right here, I'm going to go minus 39.24 newtons. And this guy here is 85 sine 55. Let's do that. 85 sine of 55. Make sure you can see that. And that's 69.6279, blah, blah, blah. I just leave it in my calculator. All right. So now I'm going to subtract that from 39.24 minus, oh, my new trick. I just go grab it from up here. There it is. Minus that and give me the answer. Okay, so my normal force is 30.38797 or 2, I guess 2. All right, so we can say it's 3.39 newtons or 3.4, 30.4. All right, so now I know what my normal force is. I got my normal force is 30.387 now. I'll probably just leave it in my calculator anyway. All right, so I got my normal force. So let's think about what we just did here. We realized that there were 2 force vectors going down. First, its own weight force. Remember that weight is really mg, plus the normal force. Because you're pushing up on it, it's pushing right back. And how do you figure what the Fn is? Well, you have to look at all the y vectors, and there was only one other one pointing up. This is why it was so important to me that you guys realize what direction these vectors are going in. So I have 1 going up, it's got to be equal to the 2 going down. So I wrote the 2 going up is equal to the 1 going down, but I'm interested in Fn. So I solved for Fn, and then I started plugging in the numbers that they are, and I come up with Fn, force, the normal force is 30.39, blah, 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 blah. I'm going to leave it in the calculator. Okay, so now we're ready for Fk. So who's Fk? Well, let's look at this picture again. And the Fk, if I'm pushing it this way, I'm pushing this guy this way. It's going this way. I neglected to draw for you. If it's going in this direction, then the force of friction has to go in the opposite direction. So here's my force, and it's moving. So it's my kinetic friction. Kinetic friction. So if you'll notice, I only have 2 vectors in the x-axis. I have Fk, and I have this one, F applied in the x direction, which is going in this direction. So I know that when it's moving, these guys, oh, because it's moving now, I have the net, the whole net thing. If it wasn't moving, they'd be equal to each other. All right, so now we're going to be using the net force equation like we did for the last problem. Let me unzoom. So the vector going to the right minus the vector going to the left is your net force, but it's also equal to ma. So let's write that over here. All right, so my net force, I've got the F applied in the x direction minus my Fk. But that happens to be equal to the mass times acceleration, Now they gave us the mass, and they also gave us the acceleration. They told us that the acceleration was 6 meters per second squared. Okay, very nice. But I'm interested in Fk, because I know what Fn is. I just solved for that. So if I solve for Fk, then I can divide them too, and there's my coefficient of kinetic friction. So let's solve for Fk right here. Oh, same thing. Add it to both sides, then subtract the ma. So F applied in the x direction minus ma is equal to Fk. So I skipped a step. I could have said plus F of k here, plus F of k here. Then I subtract ma, and then I subtract ma. Okay, so I end up with The force applied in the x direction minus the mass times acceleration is equal to my kinetic friction force. So let's plug it in. FA applied, we figured out, was 85 cosine 55. 85 cosine 55. All that subtracted to, the mass was, what's the mass? Oh, 4 kilograms. There's 4 kilograms. 4 kilograms. And the acceleration is 6 meters per second squared. 4 times 6 is 24. So that's right here is 24 newtons. All right, so now let's figure out what 85 cosine 25 is. All right, I guess I cleared it, didn't mean to. Okay, 85 cosine 50, no, there we go. 85 cosine 55. There it is, that first part there is 48.7539, whatever. Now I'm gonna subtract that by 24, 4 times 6, minus 24. There it is. So my f of k, all this is my f of k. My f of k is equal to 24.7539, etc. And because you already solved for your f of n, now we're ready to solve for mu. Mu sub k is my f sub k all over my f sub n. All right, so I solved here 24.7539 divided by 30.39, etc. Let's go grab it from the calculator. Okay, I turn off the light, but then I can't see. All right, this divided by, and let's go grab that other number, that 30 point, hope I can find it here. There it is, 3.3, that one right there. Divide those two and you get 0.814, 0.8145996, etc. All right, so that's about 0.815. There's your coefficient of kinetic friction. Okay, so that's my U sub k. All right, so I know that's a lot. Let me go through that. This one's a really interesting problem because normally things are going down ramps, but here you're pushing up. So your applied force is pushing up, even though your hand's over here probably pushing up on that, say, cell phone, something that's 8 pounds anyway, 4 kilograms. All right, so we took that applied force. I'm going to make it pink. That's the first thing you did. You draw all your vectors always on your free body diagram, and then you break it down to its components. So I have its y component right here, and I have its x component right there. Then everything else becomes kind of a tug of war, got to pay attention. How many vectors do I have in the y direction? And it's got to balance out. So that's what we did. We noticed I got 2 vectors pointing down. One is its weight, mg. There's always mg, straight down. But there's also the normal force because it's pushing up on the wall and the wall is pushing back. So I have these 2 forces that have to equal the other one that's pointing up, which I could have drawn over here as well. So I put the normal force plus the force due to gravity is equal to the applied force in the y direction. I was interested in the Fn because this equation, I need the Fn to get my coefficient of friction. So I solved for Fn, and that means I had to move things around. I only had to move that one over there, subtract over there. Then I plug things in. The applied force in the y direction is 85 times sine of 55. That was that one. Here's my mg. My mg is my mass times 9.81. Notice how this is the mg pointing down. Okay, where the other one in the horizontal direction, ma is the horizontal acceleration, or the acceleration in the horizontal direction, how fast you're accelerating across the ceiling there. So that's not the same thing as this acceleration, which is in the y direction, which is always going to be little g. All right, so that was my mg. I subtract those 2, and good, I figured out my normal force. Then I looked at my x component vectors. And so I only had the 85 cosine going to the right. And then who's opposing it? The frictional force. In this case, the kinetic friction, because it's moving. If it weren't moving, then it would be the static friction, and it'd be equal to this guy right here. But it is moving. And because it's moving, I have a net force also equal to the mass times the acceleration. All right, so then I end up with this equation that my net force, I just subtracted those 2 well, I add the two vectors. One happens to be in the negative direction, so it's like adding to a negative direction. And that's also equal to ma, the mass times acceleration. And they gave us the acceleration in the x direction. This is really acceleration in the x direction. I move things around to solve for, the only thing I'm interested in now is the kinetic force. Okay, plug in the numbers, I get the kinetic force. This is a K. Okay, now draw very nice Ks. And there's my mu. My mu, my kinetic coefficient of friction is Fk over Fn. And you plug it in and there you go. All right, again, let me know if you guys have any questions, if you want to meet with me and go through any of these problems. All right, have a good evening. Bye-bye.